Alright, so in previous class we saw how to apply single layer perceptron and multi-layer perceptron on iris dataset, and today we'll break down this MLP classifier and see what are the different components it has, as in what are the different parameters that is being used by classifier. So if you want to use MLP multi-layer perceptron, you can import it from sklearn, scikit-learn with neural network option. Okay, so that is the additional function within this class. So when you initiate it, okay, like this, so let me do that now. So if you initiate it, you will be able to see exactly what I have copy pasted here in the below cell. So you have hidden layers. So by default it is using 100 hidden layers. Okay, activation is a ReLU. We will see what ReLU is, and there is something called Adam solver, that also we will see. Alpha, batch size, okay, learning rate, and all these things one by one we will see, most of them. Okay, anyway, so starting, I recommend that you go through this article I have attached here. Again, it is a free article you can go through. Okay, so different types of neural networks. We want to understand first what type of neural network architectures exist, even before talking about the parameters. Just a overall view. So some of them we call it as feed forward neural networks. Okay, feed forward neural networks means, okay, as you can see here, it's not very clear, but anyway, so this is what feed forward neural network looks like. Typical network. Okay, so where you have these inputs, here you can immediately say there are 3 inputs in the input layer and there are 2 outputs. Okay, and anything green that you see, they are the neurons in hidden layers. Hidden layer 1, hidden layer 2. In each hidden layer there are 4 neurons and they are all interconnected. So deep feed forward neural network means it will have, there is not much difference between feed forward and deep feed forward neural network. It's just that for deep feed forward neural network there would be too many hidden layers. Okay, this is one type of network. So deep feed forward neural network, so basically this is the type of artificial network where connections between the nodes do not form a cycle. That means whatever learning is happening, it's going from left to right. Okay, so weight modification, okay, activation function calculating whether to keep the values or not. So all that is happening in one direction, left to right. So that is why we call it as deep feed forward neural network. And here you can see perceptron also. Perceptron is very simple network, as you can see, neurons and then there is output. Feed forward neural network is a simple feed forward neural network, has input layer, one hidden layer and output layer. There is no cycle anywhere, so the data flows from left to right. Same is for radial basis network, RBF. Okay, data flows from left to right. Okay, so these are very same. And multi-layer perceptron is very similar to your deep feed forward neural network. Okay, where data flows from left to right. So this is one type of network. Okay, primarily it's used for supervised learning, meaning you should have y values already so that the model can learn from them. So that is where it is used. Next type of network is convolutional neural network. In convolutional neural network, they process mainly images. They need grid like topology and they need images. Okay, so they are used on images. So basically this we will talk again in depth in next classes, but convolutional layer that are there, they will automatically detect and learn the spatial hierarchies of features, basically, and something to do with how far away the features or how closer away the features. So those things will be learned. So deep convolutional network is here, this one. Okay, so where you have input layer, hidden layers are in decreasing order and then sudden increase and then there is output. Okay, so this is deep CNN or DCN, deep convolutional neural network. and there should be another one called CNN. Look for it. um, okay, it's not. This is the one. Okay, this itself is the one. Okay, so this is a deep convolutional neural network. Next is next type of network is a recurrent neural network. Now in a recurrent neural network, in feed forward neural network and convolutional neural network, there is no memory, as in whatever the calculations happen at one layer, their output goes to the second layer, and the second layer does not remember what happens in the previous layer. Okay, it just takes the input and does its calculation, moves it back to the next layer. Okay, so that way there is no memory storage, but that is where RNN comes in. So basically what they do is they have something called gates in between layers. Okay, that is not mentioned here, but so recurrent neural networks will have something called gates that remember the previous weights. Okay, and that is why they are effective for time series. In time series, what happens? What happens in time series is you are predicting the next set of data points using the previous ones, previous series of data points. Okay, date based series, that's why it's called time series. So there are dates or months or years of data. Using that, you're going to predict what is going to happen tomorrow or in a week's time, mainly for stock forecasting. Okay, recurrent neural network are very famous for that. Okay, we have something called GRUs and LSTMs that are used for forecasting applications. So these recurrent neural networks have something called gates that remember the previous weights of previous layer, and hence they are effective for time series prediction and natural language processing. And what happens in natural language processing? Basically, you have 5 words and you are predicting the 6th word basis on the 5 words. Okay, there also it's kind of a sequence prediction. So that's why recurrent neural networks are famous there. So just look for recurrent neural networks here, or LSTMs. LSM you have, LSTM you don't have, is it? Okay, anyway, I will show you LSTM. It's not here. I kind of failed to check it. Yeah, here it is. Sorry, here they are. So this symbol that you see, cycle symbol, lock kind of symbol, that indicates they have memory. Okay, so here GRU, that is what I was saying. GRU is another type of recurrent neural network that is used for time series forecasting and natural language processing, along with LSTM. Both of these are famous for that. Okay, so these are RNNs. These are another type of networks. Next is GANs. Okay, sorry, long short term memory. Long short term memory are same as recurrent neural network, as you could see below, but they can remember, they can learn from long term dependency, as in they can remember the weights of previous layers, and they will incorporate all of that into cell state and input output gates and forget gate. There are 3 gates: input gate, output gate, and forget gate. Again, this we will learn in depth when we talk about NLPs, but for now just remember that these are another type of networks where each layer that you see, hidden layer, they have special type of gates. Okay, input gate, output gate, and forget gates. The same is true for GRUs also. Okay, so that is another type of network. Next is GANs. Now GANs are very interesting. So GANs have something called generator and discriminator. Now generator job is to generate data. Okay, and discriminator will evaluate how good the data is based as compared to the original data. Okay, so this is used for generation of images that look very similar to training data, and these GANs are the blocks. This is how generative AI took birth. using GANs only. Okay, so look for GANs here. Here, this network. Okay, so different architectures. So here you have some hidden layers, and then you have additional discriminator layers. So initially what you see is generator layer, then discriminator layer, and then you have the output. Okay, so this way you have GANs. Next is autoencoder. Autoencoder mostly are used for unsupervised learning, where you don't know whether, where some human has not evaluated whether something is true or false. Okay, so in such environments autoencoders are used. So basically they can be used for data compression. Okay, they can compress the input into lower dimensional representation, and the decoder is, see, autoencoders, they have two different mechanisms. One is called as encoder, another one is called as a decoder. The job of encoder is to compress the data, job of decoder is to reconstruct the data. So basically encoder will compress the original input that was given to it. Okay, and decoder will reconstruct the input from the original input from the whatever the compressed data is. And the idea is, if that reconstructed input, if it's very different from the very different from the original input, then we immediately call it as fraud. Okay, or we immediately identify that as a outlier kind of mechanism. Okay, so that is where autoencoders are used. Autoencoders are, they look like this, but let me see where they are. Yeah, they look very similar to this one only, where you have encoder that encodes all the data in this layer. Although this is showing, the name is showing as different, but I'm just saying autoencoders look like this. Okay, or maybe we can open it. 1 second. Autoencoder architecture. Yeah, this is what they look like. Initially the number of neurons that you have, see, this is the encoder part. It comes down to here. Okay, all the data is compressed data. Initially it compresses the data, it gives the data here, and from here it starts decoding. Decoder will start decoding the data. Okay, and finally whatever the output is obtained, it is compared to the original input that was passed here. If it is too different, then it's a fraud. If it's not too different, then it's not a fraud. Okay, all right, it looks something like this. If you want to have more layers, you can have more layers. Okay, so that way. Next type of network is transformers. Okay, the big guy. So transformers is what is being used in large language models. Okay, transformers have a way to handle the sequential data, and they're used in natural language processing. They have something called self attention mechanism. Okay, we will see what that is. And it captures, I mean, it's very complex. It can't be expressed in 2 sentences, because there is too much happening in transformer. Like multi attention is happening, positional encoding is happening, encoder is there, then decoder is there, and again even decoder is also doing the positional decoding. Okay, so all that is happening, and then on top of that there is feed forward neural network also, and then there are certain activation layers. So lot of things are happening in transformers. This we will discuss in depth in when we start the Gen AI classes. But for now, just remember that is also one layer type of network. Next is radial basis network. This is what you see here. They look very similar to your MLP networks. So these are typically used for classification and regression tasks. Okay, and they are effective in interpolation in high dimensional space. This, don't worry about all this terminology, we will look into it when we start working on the in depth of deep learning. We will revisit all this in deep learning classes, but I wanted to show you where MLP fits in. Why we are talking about MLP, I wanted to explain you. MLP is same as your radial basis network. It looks very similar to this one. Okay, but you may have additional additional layers of okay, here there is autoencoder is here. Okay, again autoencoder has various different types, like variational autoencoder, denoising autoencoder, sparse auto network. Okay, so these are all the networks. Anyway, so this is just an overview of neural networks. Now let's look at the different parameters that we saw in MLP. Okay, first parameter I would want to take is the solver. Sorry, activation function. Let's talk about activation function. Here it is, right? Activation is ReLU. Hidden layers neural networks, you already know, is just a value that you provide, okay, to determine how many neurons you want. So activation function is just a mathematical function. See, every time you hear activation function, think of it as a filter. Okay, think of it as a filter that takes some certain input and determines whether certain type of input should be allowed or not. Okay, that way every time you hear, you just equate it to filter. So basically what activation functions do is they take the input and they determine whether the output should be allowed or not, and while doing so they are introducing, this is the most important part of why we use activation function, because they introduce non-linearity into the model. So basically, even if the features are linear or non-linear, okay, so these activation functions, what they are doing is, they are doing some sort of gatekeeping, wherein which they determine whether they should allow certain input to pass or not, and by doing so they introduce non-linearity into the model. Okay, and they help learn complex patterns. Another usage is complex patterns in the data are learned because of this activation function. Maybe if there is no activation function in the neural network, then simply it will not learn complex patterns, it will fail actually. Okay, so some of the activation functions are sigmoid, the very famous sigmoid that you already learnt in logistic regression, that took a straight line and curved it into a S shape. That is exactly the same sigmoid here also. Okay, it's used for binary classification, and you already know the function 1 by 1 plus e to the power of minus x or minus z, doesn't matter. And this S shape takes the input values and maps them between 0 and 1. And again here also you can specify the threshold if you want. Okay, so this is one activation function, but you should understand that this suffers from a problem called vanishing gradient descent, vanishing gradient problems. There is another problem called exploding gradient problem. Okay, there are two different problems. One is vanishing gradient problem, another one is exploding gradient problem. This both of them we'll discuss in some time, but this is one activation function. Another activation function is tanh. Instead of sigmoid, now you can map the values between -1 and 1, and this is the formula, e to the power of x minus c minus x by, again don't worry about remembering the formulae. Okay, just know tanh takes the input, puts it between -1 and 1. Okay, so and this is preferred over sigmoid usually, because it centers the data around 0. Basically it does some sort of zero centering, and it has stronger gradients. Basically what we are saying is tanh is better than sigmoid, that's what we are saying. Okay, but notice the values, it takes the values of and maps them to -1 to 1. So this maps between 0 to 1, that is the difference. Next is the famous ReLU, rectified linear unit. Okay, so you have a linear unit. Linear unit means whatever you pass as input, it will give as same as output only. Whatever the input you pass, if you pass the straight line, it will give a straight line. That is linear unit. Rectified linear unit is you modifying that behavior by slightly little bit. What is that you are modifying is, it will check at the positive input. If the input is positive, it will allow it to be positive. Output will be also be positive. Okay, that behavior is the same as linear unit. But if the input is negative, okay, then the output will be 0. So you took the linear unit, which irrespective of the input type gives you the same output type. To that you slightly modified and you called it rectified linear unit. And rectified linear unit, if the values are positive, it will behave like linear unit only. But if the inputs are negative, it will give 0. Okay, and the formula is max of 0 comma x. If x is positive, you will get x only. If x is negative, you will get 0. Okay, so that is the behavior. It is commonly used in hidden layers of neural networks. Okay, very extensively used is ReLU only. And why? Because it solves that vanishing gradient problem. Okay, so I will explain how this problem comes in and what exactly happens. We will see that, then you will understand why what we are talking about. So it efficiently reduces that problem. That's why we use rectified linear unit. Next, there is a slight variation of ReLU also. We call it as leaky ReLU. Now what happens is, we don't want the gradients to completely disappear. Now each time I say gradient, you have to think of weights, m values, slopes. Okay, those are gradients. You are slightly modifying that m value, that itself we call it as gradients. So what this leaky ReLU does is, if the gradients are very small, so in this case or yeah, okay, so okay, understand like this. Leaky ReLU is very similar to ReLU. Let's talk about three different conditions. If the inputs are positive, ReLU allows. So does leaky ReLU also. Okay, so both leaky ReLU allow if the inputs are positive. That is common between them. Here, ReLU will output 0 if the inputs are negative. Whereas leaky ReLU, it will not give you output as 0 if the inputs are negative. Rather, it will give you it will give you a very small non-zero gradient. Okay, that is the difference. The difference between these two is, for any negative input, ReLU will give you 0 output, whereas leaky ReLU, if the input is negative, it will give you a very small 0.00 something non-zero small gradient. Okay, when the input is negative. So here we are saying, instead of 0, we are saying, okay, we will not give you 0, instead we will return 0.01. okay, 100 times smaller value of whatever the x value was. So this way, this solves another problem called dying ReLU problem, which this had. This solved vanishing gradient problem which sigmoid had. Okay, sigmoid even tanh sometimes. Okay, that's why we use ReLU. But ReLU showed another problem called dying ReLU problem, which was solved by leaky ReLU. Okay, now which is better? Leaky ReLU is the better one. So it is used to address leaky dying ReLU problem, where neurons sometimes get stuck during training. Okay, so this again we'll go in depth. I'm just giving you brief ideas so that this take this as a foundational class for deep learning as well. Okay, next is, we have variation of ReLU. Again we call it as a parametric ReLU. Here what this does is, it generalizes the leaky ReLU. So basically, each time your slope, your m values or your weights, as we call it, okay, where they are negative part, so where there is a negative part of that is generalized. Okay, leaky ReLU learns them better. That's what we are saying. So instead, look at the formula. So what we are saying is, if x is positive, if inputs are positive, both ReLU, leaky ReLU and ReLU, okay, so all these three allow it as x only. But ReLU for negative inputs gives 0. Leaky ReLU gives 100 times smaller value of x, whereas PRELU gives same as x but multiplied by alpha. Alpha is the learned parameter. Okay. Now this PRELU offers better performance compared to ReLU and leaky ReLU. Okay, better flexibility. So PRELU is better than all the above ones. Okay, again, don't equate it with sigmoid, because sigmoid is used for binary classification. These are used for different ones. So I'm comparing ReLU, leaky ReLU and PRELU. So PRELU is the better one. Next is, there is another one called ELU, exponential linear unit. Now exponential linear unit, what it does is, it uses an exponential function for negative parts. Basically it returns x if x is positive. X greater than 0 means positive only. All the numbers above 0 are positive numbers, so it will give x only, but variation is in how it's giving the value. If the numbers are negative and 0, it multiplies with the alpha. Alpha is the learning parameter, multiplied with e to power x minus 1. Okay, that's the standard value. How did it come? Don't worry about it. Okay, there is a lot of mathematics how it has come, so don't worry about it. Just remember that it multiplies lambda into e to power x minus 1 if x less than or equal to 0, smaller, less than or equal to 0. So this helps in faster and more accurate learning, and also solves the problem of dying ReLU. Okay. Next activation function we use is softmax. Softmax is, if you use sigmoid for binary classification, you have to use softmax for multi-class classification. Okay. Now the formula is e to power of x of I by summation of e to power of x of j. Okay. So don't worry about the formula, and don't worry much. Okay, wherever you can remember the formula, remember. If you are not able to remember, that's okay. Nobody even in interview will not ask you to give the formula, tell the formula. They will rather ask you to explain how they may differ, how they are used, what are the use cases, but no one will ask you the formula. Okay, it's humanly not possible, that's what I'm saying. Anyway, so next one is, this is used in output layer of the neural network for multi-class classification. Okay, again we'll revisit all these topics in deep learning, but for now, just as a foundational class, just remember this. And multi-layer perceptron is using all these activations. One of these activations, if I open the documentation again, if you scroll down, look at the activation functions that it is using. Identity means it will no op activation. So basically very same as f of x equals to x. That means there is no activation only there. Identity means no activation function. So okay, logistic means sigmoid. Sigmoid and logistic, they are interchangeable. Okay. So next is tanh. Tanh it uses, ReLU it uses. Now if it uses ReLU, if you want to use leaky ReLU, then you have to write your own function and use it as an activation function in the layer. Okay, I think when they invented this MLP, I don't think there was a leaky ReLU or PRELU or ELU. Okay, maybe that's why they don't have that implementation, but if you want to use it, you can use it. These are the only options that you have in MLP. Okay, multi-layer perceptron. Next we will look at the second topic, solver. Now this is the topic where most of us fail. Okay, because there is too much is happening in solvers. So solvers we usually call as optimization algorithms. Optimization algorithms, the job of all these algorithms is to minimize the loss or minimize the error. Now what is error? Error is if your original value was 5, if your model is predicting 3, now the error is 5 minus 3, 2. 2 is the error. So we also call errors as residuals. Your job is to minimize this loss function, and loss function in turn minimizes residual, and these solvers are optimizing this phenomena. Okay, during training, all this is happening during training. Okay, So most famous, or most not famous exactly, most easily rememberable, I should say, is the stochastic gradient descent. We already learned this. If you recall, Hessian matrix, curvature of cost function, randomly initialized m values, and then there is learning parameter. So all that, if you recall, that is what the stochastic gradient descent is. Basically, again, I don't want to go in depth here. I will revisit this in deep learning class. So one of the solver is stochastic gradient descent. What it does is, it starts updating the model parameters for each training example. Very important, this distinction is very important. It happens at each training example, whereas mini batch gradient descent happens for couple of, or let's just say 10, 12, 14, sorry, not exactly 10, 12, in the multiples of 2, like 8, 16, 32 batches of training examples. Okay, that is the difference. Here it is updating the model parameters for each training row. Here it is updating the parameters for small batches. So basically it takes small batch of rows of data, then it calculates that whatever it does, okay, gradient descent, and likewise then it picks the next set of batches. Whereas stochastic gradient descent takes one row at a time. Okay. So description is, so basically understand that gradient calculation that we have already learned for logistic regression. Just remember all of that here. Next is advantages, is very simple to implement, well suited for large data set, avoids local minima. Local minima, global minima, again I will talk about those. There is a problem called local minima. Okay, so it avoids the local minima. That is one good advantage of it. Next is, it balances between stochastic gradient descent and batch gradient descent for more, and it exhibits more stable updates. Disadvantage is it's slow. Why it's slow? Very simple. It's taking one example at a time. Okay, and high variance in updates. High variance in updates because one row of data could be different from another row. No. Okay, so that's why you have lot of variance. So here it still requires hyperparameter tuning, and it can be computationally expensive. That is a disadvantage of mini batch. When to use stochastic gradient descent? When you have large data set or for online learning. Okay, and this is used when you have lot of computational resources, but this does the convergence faster, quicker convergence. Okay, next is batch gradient descent. One is mini batch, okay, another one is batch. Here batch gradient descent takes the entire data set in one go. Okay, this exhibits stable convergence, low variance. That is another advantage, but it requires large memory. Why? Because it takes entire data in one go to compute the what? Gradients. Okay, to compute the gradients. Again, each time I say gradient, I want you to imagine the slopes or weights with minor differences between the gradients. Okay, that gradient formula you have to remember, delta m minus alpha into m minus alpha into delta m. Small variation of m value is subtracted. So that is what gradient we are dealing with. Okay, and when to use? When working with small data sets and you want a stable convergence. Okay, so this is not usable for large data sets. If your training data set is huge, don't use batch gradient. Okay, next is momentum. Now momentum also does one additional thing, in that basically momentum is used to accelerate the convergence. Okay, basically what you do is you take the past gradients and you come up with a smooth parameter learning line. Okay, and how it works is, it again we'll learn this in next class, because if I start explaining again, everything will become mathematical and complex. For now let's park it. Okay, just know the names for now. Next is accelerates convergence, reduces oscillations. Basically, when you keep on multiplying your learning parameter, which is your alpha, with the slopes and subtract them from the subtract that product term from the original weights, you tend to oscillate. First it goes left, right in the curvature of the cost function. Imagine cost function as a fabric held by four people in a very, or maybe imagine, how do I put it, um, yeah, cost function each. Okay, let me see if I can get the cost function somewhere here. I have drawn, no, here, not here. Okay, I don't have the cost function curvature here, but I will show you. um, Maybe for the iris class, did we show that in the previous class by any chance? No. Okay, I don't think we saw that in the previous class. Okay, anyway, but in, I remember showing that in logistic regression. It's just the curvature. When you start changing the value of m, it will appear as though it, oscillates. That oscillation is reduced by this momentum. Okay. Uh, Sometimes it may overshoot. Okay, and this also requires hyperparameter tuning. If you want to speed up the learning process, then you have to use the momentum. Okay, just remember this much: momentum is used to speed up the training part. Next, there is another one called nag. We almost never use this, honestly. So this is a variant of momentum that looks ahead to correct the gradients. Faster convergence reduces overshooting. This overshoot, no momentum, that disadvantage is taken care by nag. This also requires careful hyperparameter tuning. Sorry, give it a minute. Sorry, some jet is flying at very low distance. Okay, next is, when training deep neural network with high dimensional data, we can use NAC. Okay. So next is ADA-grad. ADA-grad has learning parameter, learning rate as we call. Okay. So this adapts to the learning rate throughout the curvature of the function. So sometimes you need to have a learning rate, quicker learning rate, sometimes slower learning rate, so that so to that it adapts. How it does, we'll see in the next deep learning class. This requires less tuning, works well with sparse data. Sparse data means, if you imagine data as a matrix, if you have too many zeros in the matrix, that is called as sparse data. Okay. Dense data means if you have non-zero values in the matrix. Imagine 10 by 10 matrix in which at least 7 layers are 0, then it is sparse data. At least if one layer is 0, it's still dense data only. Okay, so data where the values are non-zero is called as dense data, whereas too many zeros, sparse data. Now in real life, lot of data is sparse data. Okay, so ADA-grad is works well with on that type of data, but it also suffers from another disadvantage called learning rate can decay. There is something called a learning rate decay problem that we will again see. So that problem is a disadvantage, and you should use this when you, in the input data, if you see there are too many zero values and if the data is non-stationary, okay, then you can use the ADA-grad. Next is RMS prop. Okay, basically RMS prop uses something called, it maintains a moving average of squared gradients. Okay, root mean squared. Okay, so that is what RMS is for, root mean squared propagation. Okay, root mean squared propagation, RMS prop. So it means instead of only calculating the gradient, it will calculate the moving average of squared gradients. This helps in adapting to various learning rates, and it is effective for non-stationary objectives and prevents learning rate decay. So whatever the problem suffered by ADA-grad is solved by RMS prop. Okay, this also requires careful hyperparameter tuning and very difficult to understand. And you should use it when you work with recurrent neural networks or any noisy data. If you have an image let's just say you are working on CCTV footage images where they are blurry, there is too much noise or there are some sort of filters, then you should use RMS prop to remove those noise. Okay, yeah, the most famous one, Adam. Okay, adaptive moment estimation. Moment, okay, the moment was, it used to speed up the convergence. That is where why we used moment. Now we are using a variation of that moment, we are calling it as adaptive moment estimation. Okay, so this combines the advantages of both RMS prop and momentum. Okay, so here what it does is, it delivers fast convergence, robust to noisy data. This also requires hyperparameter tuning, and sometimes it's computationally expensive, and you should use it for complex tasks. If you have very high dimensional data, you should use Adam without even second thoughts. And that's why, because it is so good, that is used as by default solver in MLP also. Not only MLP, it's used as by default solver in multiple various other places. Okay, next one is ADA delta. It's an extension of ADA grad, this one. Okay, but no, notice it, remember, it suffers from learning rate. So basically, extension of ADA grads, it seeks to reduce the aggressive decreasing learning rate. Basically, it's trying to solve the learning decay problem. Okay, it solves that. And next is, we don't have to manually set a learning rate. That is the big advantage, and it is suited for large neural networks. It can be computationally intensive, that means very high cost. Next is working with large neural networks and dynamic tasks that change, like your videos. Okay, in the video data, if the data keeps on dynamically changing, okay, like your video data, or let's just say your stock prediction, stocks keep on going up down. Okay, so unpredictable basically, so there you can use ADA delta. Next is ADA max, variation of Adam. Okay, so basically variation of Adam, we use it something called infinity norm here. Okay, the slight variation to Adam. This performs well on large scale data, more stable. Okay, but this also has similar disadvantages as Adam, that nothing but it's computationally expensive, and you should use it when you work on large data set, and where you think Adam is not performing well, you should use Adam max. Okay, understood? Clear up until this point? Give me a thumbs up, or no, say yes. These, if you understood these activation functions and solvers, then you understood 80% of neural network. That's how I see it, because every other topic is a very minor and very easy to remember topic. These are the ones where a lot of complexity is there. Okay, next topic we want to discuss is alpha. Alpha is strength of L2 regularization. Okay, so multi-layer perceptron, just like your logistic regression, they use regularization called lasso and ridge regression. Basically, this parameter tunes that alpha parameter. If you set it to closer to 0, okay, then it allows the model to fit training data more closely. It captures the complex patterns, and you will end up overfitting. Okay, it may not perform well on new data. So that is a disadvantage. It will learn the training data very well, but it will not perform well on the new data. Okay, so you have to use it when you can, when you see the overfitting chances are very low. Okay, so that is when you should use it. Moderate alpha, it provides a balance between bias and variance. It may not capture complex patterns, but it will work both well on training and validation data. If you set high alpha, that means you are adding very strong regularization. It will prevent overfitting, but it may, it will suffer from underfitting. Okay, so it may lead to better generalization as well, but sometimes it may do underfitting. Okay, when the model is too simple to capture patterns. Nothing but, see, what is this uh, overfitting and underfitting? Overfitting and underfitting. Okay, overfitting is the condition where you see high training accuracy, okay, and low testing accuracy. On new data, that is on new test data, it won't perform well. Okay, so that is what overfitting is. Underfitting is, okay, so this is underfitting. Underfitting means it won't learn training data as well as testing data. Sorry, this is testing data. Okay, so neither, it won't learn anything. So that's what the condition is, that's what we are saying. So understood alpha parameter. So you have to keep it somewhere moderate to get best of both worlds. Okay, next is batch size. How should you decide the batch size? Okay, typically if you have too many rows of data, okay, when to use, first look at the when to use. Small size you should use when you have limited computational resources, nothing but when you have limited memory, and if you are aiming for better generalization, then you should small batch size. And what is that small batch size? 1 to 32. May it be video data, may it be image data, may it be tabular data, whatever it is, you should use small number if you have limited memory. Okay, limited memory and limited CPU clock cycles. Anyway, so this is because you are using small batch sizes. To reach one epoch, it takes a lot of time because it has to pick data in batches. Okay, and there are frequent updates to the weights, hence there is better generalization, but that also involves noisier gradient estimates. Okay, there is some noise also. Okay, that you have to keep in mind. Medium batch size you should use when you want stability in the results and computational efficiency. Okay, this number could be 32 to 256, and when you are aiming for a balance between convergence speed and generalization, you should use medium. Large batch size you should use if you have high sufficient computational resources and you want faster execution. That is when you should use it. For example, your large language models training, you want faster convergence because you can't run the model each day. If you run, you are adding few millions or few hundred thousands of dollars in GPU compute costs. So you want faster execution, you can use large batch size. Okay, so faster convergence per epoch, more efficient computation, example GPUs. Okay, and it will arrive. Now look at the disadvantages. First one gives the disadvantage as lower convergence, higher computational cost, because if you're picking small amount of data, then you will have to run the model for a long time. So per epoch cost is high. This is optimal, and this is for large batch size, it may overfit and requires more memory, less frequent updates. It may lead to poor generalization. Okay, here good generalization, here poor generalization. So always pick the medium batch size, but again depends on the use case what it should be. Okay, if you have smaller amount of rows, let's just say you have 1000 rows only, and you don't have enough compute, then go for this. If you have enough compute, go for this. Okay, that way you can choose the batch size. Batch size is one of the parameters here. Automatically, if you set it to automatically, model will decide. Okay, if you set it to automatic, model will decide what should be the, where is that, yeah, it will decide based on the solver. It will decide what to choose. For example, LBFGS, this is what we discussed now. LBFGS will not use mini batch. Okay, and when you set it to auto, it will pick 200 amount of rows. Okay, typically, but that also depends on the samples. So let's just say samples are 180, it will pick 180 only minimum. That's why we are saying minimum number of whatever this is. Let's just say samples are 1000, then it will pick 200. Let's just say samples are 201, now what, it will still pick 200 only. Okay, let's just say samples are 199, it will pick 199. Okay, it will pick 199 here. Let's just say samples of 10,000, it will pick 200. So that way minimum number it will pick. Okay, hope this is clear. So these are the topics, important topics. We'll move on to next topic, but I want you to take a quick break. I want to pause here and please come back in 10 minutes. Okay, take 10 minutes.